Welcome to my talk and thanks for coming, I appreciate it. Today we're going to talk about parallel range algorithms. Let me first introduce myself. I am known in the committee, but I'm new on this conference and I'll try to do it very quickly. So my name is Ruslan. Somebody calls me Ruslan, that's fine. Please know Ruslan, and all of that. I'm working for Intel. I'm oneAPI, the data parallel C++ or just oneDPL lead developer, and this is our implementation of parallel algorithms. I mean Intel. I have significant contributions to other threading models within Intel, including TBB, or like oneAPI threading building blocks as the full name, but not only. In the past, I was contributor to SQL. This is, the standard, which is the Kronos one, held by Kronos, and it's for heterogeneous computing. I mean, I can come back at some point if necessary, but this is not my focus for now. And also, I have contributions to C++ standard, mostly focusing on std, state execution, and parallelism. More than that, but mostly focusing on this. I already have 8 accepted proposals. I hope the proposal we are going to talk today is going to be 9th. And by the way, I'm also SG1, Concurrency and Parallelism co-chair in C++ Standard Committee. That's who I am, but that's the work perspective. I'm also a pretty good singer. I'm a bad guitar player, and the picture of the guitar without me is not because I'm bad, because I don't have a good picture with the guitar and with myself. Recently, I became a father. My son is almost 1 year old. Thanks. And I'm a mountain biker. Yeah, that's me trying to climb. Also don't have a better picture, but you see the beautifulness of Colorado. But let's talk not about me, unfortunately. This talk is about parallel range algorithms. So let's first say what are parallel algorithms in general. So we added them in C++ 17, and those algorithms are with the first template parameter named execution policy, instead namespace, and taken iterators. And the example is on the screen. So if the code looks too small to you, I just encourage you guys to move closer. The thing is, I cannot transform it in parallel because we don't have parallel transform algorithms with ranges. So, yeah, you can see the serial code, which is has just some input, begin and end, and some predicate to find. And also you have a parallel code, and which just differs by adding a first state execution policy argument, which is par in our case, that meaning that this code is allowed to be parallelized. And if I'm going too fast, so also tell me. What is parallel range algorithms? So it's our proposal with P3179, and it's also with the first template parameter, which is constrained by the exposition-only execution policy concept in ranges namespace, and we have overloads. One of them takes ranges, and another one takes iterators and sentinels. And here's an example. As you can see, we also have find if with some input and predicate. And with our proposal, the only things that differs is adding the execution policy of first argument. And that's basically it. This is the whole proposal. This is the whole talk. Thank you for coming. And for the record, I have not stolen this joke from Sean Parent. We just, just simultaneously,
We're equally brilliant.
Yeah. Okay. Let's stick to that. I like that. Okay. So, of course, it's not that simple. Otherwise, I mean, it would be just a slam dunk paper, but the paper is huge and it explains a lot. Because, about the design, because the new versions of algorithms, the parallel ones, is the evolution. But first, let's talk about motivation. Our motivation to do that is because, all our algorithms today, I mean parallel ones, are blocking. So before you can call the next one, you basically need to wait until the previous one is finished. But now with ranges, since they, this is not to talk about ranges, I hope you guys know that it's, maybe lazy evaluated pipeline. You can basically fuse some parallel algorithms called in one and parallelize only one, and that's less overhead, potentially. It's better expressiveness and productivity of the parallel code, and it's ease of use. There is one hidden motivation, which you're going to see later. But let's first look at the example. The example is we use some transformation. We have, again, like with existing algorithms, with C++ parallel algorithms, which is like execution policy, then begin and end of some data, the output, which is result. Then we do some transformation. We do some reverse. So after transformation, we reverse this data. And we also do some, we do find if, like for some predicate. And what we can see that we have 3 algorithm invocations, and each adds its own overhead for like each new parallel region call. That's one thing. As I mentioned, you need to wait before the next one completes, before calling the, the previous one completes before calling the next one. But also for find if, we try to find, the leftmost position that satisfies like our predicate. But if we imagine the memory to be like going from left to right, if you find something on the middle, potentially all the work from the right can be already cancelled. We don't need to look there. I mean, if it's possible to cancel it, like depending on your threading framework, you just send the cancellation there, and you can continue just searching on the left. If it's the leftmost, we're done. We can send the cancellation like to the rest of it, but only for the third algorithm call. You need to finish transform and reverse before that. And to be honest, this example is a little bit of artificial, because potentially we could, I mean, if we have like find if last, which we have since C++20, we could replace all of this with just one invocation call and move the like transformation to the predicate for find if. But there is a very specific reason why this example is like this. And the reason is here. So I'm showing the same code with fancy iterators. And from the fancy iterators perspective, we have reverse and transform. I mean, the transform iterator not in the standard, but we have it like in third-party libraries, like oneDPL again from Intel, NVIDIA Thrust. We have transform iterator there. And the thing is, we also have reverse and transform view, So it's just easy to show how we go from the C++17 code to the ranges code with this example, because we can replace it with both fancy iterators, how we call them, and with views. Isn't that code look awful? From my perspective, it is. Because there are several interesting things here. Like, yes, you also kind of build the pipeline. You build it, but like in reverse order, not in natural order. So first of all, you're going to dereference data, then transform iterator, and then reverse. So yeah, you could construct ranges the same way, but this is on fancy iterator, but the ranges have the pipeline syntax. Fancy iterators do not. And you can see like there is a one like DPL namespace indicating that that comes from another library. And another point here, I mean, yes, we achieve our goal. Like it's one invocation call. We like do everything on the flight lazily. We only parallelize find if, and unnecessary word might be skipped to the right of the found element. But again, we don't like this code, at least how I get the feeling of the room. It's a lot of verbosity, and the things to keep in mind that end becomes, like the end of data becomes the begin of reverse iterator. Even worse, it becomes the end of transform iterator, because you further wrap it in reverse iterator. And this is kind of all the things that you need to keep in mind that it's not natural. But there is another problem in this code. It doesn't compile. Guess why?
Rob? Lambda types are different?
The lambda types are different, exactly. So basically, the end for findIf technically doesn't need lambda. Only the begin needs that, but this is our interface. So we have findIf, which has the same type, like one template parameter for both first and last. We have transform iterator. I mean, it's just, you know, to give you an idea how the interface looks like. So the function becomes the part, like the function type becomes the part of the transform iterator itself. And then we do make transform iterator with the like lambdas, which looks exactly the same, but we know that we are going to get the compile time error because we have conflicting deducing type for forwarded template parameter of findIf, because actually we have like different lambda types, and thus we have different transform iterator types. With that, you know, of course, lambda 1 and lambda 2 are just like some types. We don't know them. It's just to show that they're different. We don't know the exact types. Let's get back to this slide. The fix is obvious and simple. We just extract lambda to the variable. Now it has one type. We just add it, but again, it's still ugly, and that's not what we like. So basically, we can do a pipeline and parallel invocation with existing CppNow algorithms. This is the pipeline, basically the same. Like you do data, you do transform, you do reverse, and then you pass like it as a begin and end to findIf. And I believe, if I'm not mistaken, that was your paper, David, that allows that.
Yes, it allows the ranges to be used in the existing libraries.
Thank you for that, but it achieves the goal, and it was a quick solution, but from my perspective, still unnecessarily verbose. I mean, it works, yes. I mean, unless we have something better. So here's an example that I really like. We have a findIf with policy. We have our pipeline, data, transform, reverse, and then predicate. Again, the same bullets, it achieves the goal. There is a problem though. Does anybody see the problem? Result is unusable. Because, I mean, of course, like I'm not allowed to dereference it like that. You need to check if it, like, if findIf actually finds something. But it's just to show that any operation that you try to do on the result becomes a compilation error. Because transform view is not borrowed range. We don't have Zach here, but I hope he will fix that. I mean, he has a paper. So he's working on that. But that's the point. Like, we cannot just pass our value pipeline, which is we see here, and then just use the result. So we still need to extract it in its own variable to make it L value. But it's still, you know, more or less nice code from my perspective. You store it, and then you use this pipeline as the policy, pipeline, and predict. That's basically it. We achieve our goal. It's still concise. I like this example. And this is the hidden motivation. We have the ability to use the projections. This is the difference from the existing C++17 algorithms, even though we can use pipelines with them today. Okay. I hope everything is clear so far. If not, it's good time to ask questions. But if there are no other questions, let's go to key difference to existing algorithms. And mostly we're talking about the differences to serial range algorithm, but there is an intersection between like difference to serial range algorithms and existing one like C++17 and even before. And the first difference is we add an execution policy. Isn't that obvious? Yes, it's not like complicated, and that was almost immediately accepted. The next thing is we want parallel algorithms. the new one that we propose, to require random access, iterator, or range, depending on the overload. The next one is parallel algorithms require sized range right now, like the new ones again. And parallel range algorithms take a range as the output, not an iterator. And also, the overload with iterators and sentinels takes additional output sentinel. This is the biggest one, but in combination with the previous one, with C, requiring sized ranges, it gives us the opportunity to, be more memory safe and also be more performant. Jeff.
So going back to the execution policy for a moment, obviously that was a decision that was made in 2017, right? Or like
even earlier in TS.
Similar decision was made there, right? And I don't know what was the motivation there, right? Like there's just no way to say under the hood, just make that algorithm parallel when it's okay to?
No, because the compiler cannot detect when it's okay.
Yes.
It's a promise made by the user that their code does not do anything. That's not
like everybody.
That's thread unsafe.
Like
the compiler cannot. Sorry.
So a lot of people in the committee like confused by execution policy meaning. I like to think about the execution policy as the permission and the property of the lambda. The user gives the permission what is allowed to do with this lambda. And par basically means it's safe to parallelize. Do the best you can. Like seek means it's as strict as possible. You have to, the algorithm implementer have to execute it sequentially.
Okay, that's an interesting point because I can see in 2017 when concepts are not in the language, right? You couldn't say anything necessarily about the type that is going to be manipulated in this range.
Okay.
But of course, now you could reach in and figure out what the types are. I mean, so like you could probably figure out whether or not it's trivially.
No, because you don't know if there is a mutex in your lambda. You just don't know it.
No. The lambda part I get. And I understand why it's there now.
Okay.
Which I didn't until 1 second ago.
Okay.
But the fact that I was thinking it would be about the types and not about the lambda, but that's interesting.
Yeah.
Saying basically that the property of being able to parallel would be of the type.
I'm happy to discuss the properties of execution policy after this talk with anybody who wants to discuss it with me, but this is not a talk about execution policy, so let's not stick to that until we. Yes, and I hope I answered your question. Yeah. So we're going to look on all those like design decisions later, why we made that, why we believe it's important. But now let's just look at the differences. So this is existing algorithms, and I took transform. Not binary transform, by the way, just unary transform, to show you the existing overload. Isn't that fascinating? How much concepts we already have? Let's make it even worse. So first of all, you see the iterator and sentinel overload and range overload. What we do, we add an execution policy parameter, which is function parameter, and template parameter, which is constrained by the execution policy exposition only concept. And you can see that, it's just std is execution policy V with std remove cvref T of our execution policy. Then we change the input. We say that it's random access iterator for input. Also, we change the output for the first overload, but we don't touch the second one. So it's random access iterator for the output of the first overload, and it's random access range for the overload with ranges. Then we touched sized part of it. So we say for the first overload, it's sized sentinel for the input. And we combine random access and sized in one concept, as we discussed in library working group, one of the feedback on the wording. So, and it's also one of the exposition only concepts that just combines the property of random access range and sized range. And this is our range as the output thing, which basically says that, okay, let's look at the ranges overload first. We add this range as the output. We also use we extract iterator with some traits, and we also say that, okay, now our output is range, not the iterator. And we also say add yet another size sentinel for the iterator and sentinel overload. And to show you just, side by side, or better to say top to bottom comparison, you can see the serial iterator and sentinel overload and the parallel one, and you can see all the differences. So execution policy, random access iterator, sided sentinel for input, random access iterator for output, sided sentinel for output, and execution policy, function parameter, and sentinel for the output function parameter. And this is for ranges. So more or less the same thing, but instead of iterators and sentinels, we're using ranges. Okay, we're good now. Let's move on. Let's talk in more details why we chose this design. First of all, let's talk about sized random access range, and let's talk about random access part of it. What we learned from C++17 is the most implementations I'm aware of use random access iterators, while C++17 algorithms require forward iterator. For the vast majority of algorithms, we don't take sort into account. Sort, even serial sort, requires random access. And only Microsoft STL supports forward iterator. And there is an asterisk there, and that's again to know that from the implementation that I've studied. I cannot say for sure. oneDPL also sort of supported for one algorithm, but not really, and the performance is definitely going to be worse. So the thing is, I talked with one, when C++17 algorithms were accepted, I talked with one of the committee members and asked, why is that forward iterator, by the way? And the answer was, I might not remember that correctly, but I think it was even input iterator. And the last minute before landing it to C++ standard, that was a question, why is that input iterator, by the way, what's the point of, making it input iterator for parallelism? And the answer was, yeah, let's make it forward, should be good enough. And that's how it happened. And and I'm not sure if it's true story or not, but what I did, I found the old parallelism TS, where there was a transform reduce, the parallel one, with input iterator, so I kind of believe in that story. So the point is, seems like nobody really deeply thought about that at that period of time. So we are going to fix that with the new set, overload set. Yeah.
I don't understand why you're upset about. Shouldn't an algorithm require the least, the most restrictive? A forward iterator is an input iterator.
Yes.
Random access iterator is a forward iterator.
Yes.
So if the library requires a forward iterator, you can't pass a random access iterator.
Yeah, I know.
So you say, okay, you have a subset that requires a more restrictive iterator. But that's nothing against the original
But what about the algorithm?
Yeah, the point is, it's not suitable for parallelization. When you just pass the forward iterator, yes, it works, but it silently compiles, and the performance is bad. And everybody complains about that because they don't know how to understand it. There is no efficient way to parallelize all the algorithms in the standard library with just forward iterators.
But the flip side is, if I don't want to parallelize, I shouldn't be required to give you a random access iterator.
Use see
There's overload.
Yeah, there are overloads.
So you're adding a new overload, but that's not. There's no reason to complain about the original standard.
No, I'm complaining about original parallel algorithms again.
Parallel. Sorry.
Yes. Yes. As you can see, C++17 parallel algorithms required.
Sorry, my bad.
Okay. So random access iterator is the best abstraction that we have for now. And this is the key point for now. So we were debating back and forth whether we should support something that is like something like filter view. That might be useful, yes, I admit it. But its performance is yet to be proven. At least we don't have any implementation. And we kind of think that it might be relaxed on the future, but not with something that exists in the standard today, but with something else, like more relaxed than random access iterator, but still better than just bidirectional, let's say. And the size part of it, we basically need to know in parallel world the size in advance for two main reasons, let's say. It's memory safety. We are not going to write out of bounds because we also know that the size of the output. And we will look into that in combination with range as the output. And we also, for performance reasons, if we know that our output is less than input, we can basically, check it in advance because it's random access and sized and do the work that output allows us. And that's it. We're done here. So let's go to range as the output. We have a very interesting discussion. So basically, this is the code name of our design choice. Please don't mix it with output range. Output range is the concept in C++. Range is the output, is the way how you pass the output to the algorithms. And I'm starting introducing categories because at the end I want to show you which algorithms fit into this category, but it's closer to the end of the talk. So algorithm with output. What advantages we've got of it? So first of all, it's ease of use. You don't need to write std ranges begin for the output or output.begin. Then it's better memory safety. As I said, you're not going to write out of bounds. It's potentially better performance, and potentially I'm saying because it depends on the algorithm. For example, for something similar to for each, copy, transform, yes, you can just check if your output is less, you can just do this number of operations. For copy, if let's say it's more complicated, it depends. But in some cases, I think you also can get a better performance. And also we have an ability to detect an error. And here I mean logical error. So it's not like we pass insufficient amount of output to embrace all the input data and it's undefined behavior. No, it's not the case right now. We can detect that and we can check it in the code if it was a mistake or not. The objection was more complicated switch between serial and parallel algorithms. I mean, this is true, yes. Inconsistency with serial range algorithms. Sure. C++ standard is absolutely 100% consistent in a single, in every single place. For sure. Yeah, we will look into that.
Is a long time.
Yeah, I mean, sarcasm, yeah. We will look into that. And unclear semantics. Specifically, we had this conversation with Jonathan, what we would do with std ranges copy, but we will look into that in a minute as well. So first of all, let me tell you that the evolution is something that we, make some even inconsistent proposals when we learn from the past. And it's not only for output, let's just consider binary transform, which is has the last for the first input. It's binary transform, but it doesn't have last two for the second input. And we just rely on the fact that first two should be none less than the size of the first sequence. The thing is, and this is serial algorithm, as you can see, and the transform, the serial one, but with ranges, already adds sentinel for the second input, and also for the ranges overload, the second input is range. And guess what? It goes to the minimal one. So whatever exhausted first, it's done basically. Whatever input is smaller. So yeah, we already have if you want like more complicated switch from existing from this old version of serial algorithms to modern version of serial algorithms. Okay, let's talk about, first of all, our consistency. We have copy, which has iterator as an output. I mean, strictly speaking, it's weakly incrementable, but semantically, let's think about it like as an iterator. And the same for ranges overload. And I mean, yeah, we assume that the output should be sufficient to, take all the elements from input. But we have uninitialized copy, which is, I mean, very similar algorithm, but instead of assigning, it constructs. And now we have range as an output for the ranges overload and the sentinel for the output as well. So we're already inconsistent. And I'm not sure why is that, because, basically they were added at the same time as far as I'm aware. Jonathan, please.
Yeah, so my theory on why this is, it's not explicitly written in the paper. I tried digging that up when we discussed it. So the serial ranges copy allows like a back inserter as an output.
Okay.
Whereas the uninitialized copy does not.
Okay.
And so if it does not allow a back inserter, then you don't lose anything by requiring the sentinel.
Okay.
Instead you gain the safety. And so that is why I'm assuming that.
Okay. Yeah, that makes sense. And also it's not applicable for us, for our proposal, because we propose random access iterator and it already doesn't allow like back inserter. So, and unclear semantics. So the question for this code, when we have like the input, which is like the size of 5 and the output, which is size of 3, what's going to happen with V2? Is it like full copy or is it not? Like what happens? But it might appear that the copy algorithm allocates for V2, so it's like expands the capacity of the vector. I mean, yes, it might appear that way, but our proposal is to execute an algorithm with the output like until we meet like the smaller range. And this is consistent with all the algorithms we have, as far as I can tell. If I'm not mistaken, we never change the capacity of any inputs or outputs of the algorithm. So yes, it might allocate internally, but for some computations, like some temporary buffers, but not changing the user data that comes from outside. And again, we have algorithm with exactly the same semantics. Uninitialized copy does it. So it just, if output is less, it goes till the output is exhausted. But not honestly, we have the algorithm. We have algorithms. We have uninitialized move and partial sort copy as well with the same semantics. Partial sort copy is a little bit different because there the range as an output allows you to also set a bound till which you're going to do your partial sort. But still, the precedent is there. Okay. So I believe that going back to this slide with like pros and objection, we just eliminate two of those, at least on the C++ committee level. We were able to convince them that it's the right thing to do for parallel algorithms. Yes, it's still more complicated switch, but it's an evolution, and we even wrote a separate proposal that explains our view on ranges and output design aspect in details. So if you want to learn more, I just encourage you to go and read it. I have like some useful links at the end. Okay, let's talk about interesting and more complicated part. So we have reverse copy and rotate copy. And those are special algorithms. I don't know how to categorize them better. And you will see where this, specialty comes from. So reverse copy has the following interface. So we have like range, like execution policy, range as and range as an output. let's imagine that this is not the parallel algorithm, but the existing one. What do you think it returns for the input? I mean, like as this borrowed iterator. And again, like I'm talking about the existing one, the serial one. What does it return? What value?
The value of the iterator when it ended.
That's how I would design it. Okay. But it always returns last. I mean, the iterator that is equal to last. And this design, I mean, it kind of makes sense because all the ends, I mean, the end of the algorithm is a sentinel. So it's not the iterator. So even stood for each, where you have both like begin and end, always returns you an iterator back. And the reason for that is because you probably want the iterator when the algorithm ends, because you might not have it. You might still have a sentinel. So I can see this design choice, but I would do what David says. And yeah, so let's see what we propose. Basically, if we have the vector, like which is input as the size of 4, and the output which is like can take only 2 elements, what's going to happen? So the output after the algorithm's execution is 4 and 3. I mean, it's logical. We come from an end, and we take all that we can, but also we return the iterator that points to the position, like to the last element that we copied. And in that case, it's 3, right? Like it points to the element which is equal 3. And it might seem awkward at the first glance, but there is a logic behind that. When you, like, first of all, it's kind of, when you basically try to check what was copied, you take input begin and also res.in, which is the input that algorithm returns, and you get the exact range that was not copied. So if you say like res.in minus input begin, it's 2. And you understand that first, like element that equal 1 and element that equal 2 were not copied. That's how users can detect it if it was an error or if it was intentional. If it's enough, like if it have the output size 4, we just copy it in reverse as expected, 4, 3, 2, 1, and we return the begin, like without like reading everything on the slide, but in principle the begin of input. Because it's an empty range, we were able to copy everything. Sorry. And if we do an emulation with the existing like algorithms and views, we do copy and we do like pipe on the input, like we do reverse and we do take 2. The behavior is exactly as we propose. So reverse with copy with reverse view works the same way. The only difference is when you just wrap it with reverse, you're going to get back reverse iterator, not the like original data one. But then how reverse iterator works, it basically adds the -1 on the dereference, and then reverse iterator would point to the element 2, but it's not comparable with the input end. Those are different types. Input end is, the original type, which is like vector in our case, and the reverse iterator is just different type. So you need to take base, and the base of reverse iterator would point to the same element. So that's why we claim that the behavior is the same. But this is the emulation for the input. Let's emulate for the output. We have an initialized copy. So we just allocate some memory for override. We create subrange. We do input in reverse and take only 2 from, from the output. Again, long story short, the behavior is the same. Yes, you get back the reverse iterator, but when you say like res.in.base and compare it with the input.end, it would point you to the same behavior that we propose. So right now in the standard, we have inconsistent behavior between reverse copy and copy with reverse view. With our proposal, with parallel range algorithms, you're going to have a consistent behavior. I believe it's improvement. There might be multiple viewpoints on that. And also that means that we return last, like we have a different semantics from serial algorithms. They return last always because they always assume the input is sufficient. We return last only if the output is empty. So we did not do any manipulations. That's the implication of our design choices. Okay, let's talk about rotate copy. It's even more special. So for us, it was like, remove it from like one of the revisions and then immediately get it back in the next revision and see how it goes in LEWG, in library evolution. What's so special about rotate? So rotate basically has the range and the middle of this range, and it copies the data to the output from middle to r.end, and like non-inclusively, of course, and then from r begin to middle. Again, middle in that case not inclusive. So the simplest implementation that we can imagine for rotate is like stat copy from middle to end, and the output is like result r begin, and stat copy from begin to middle, and again like the result, like the output is like result plus the copied element from the first invocation. But then guess what it returns? I mean the serial one, the existing one, for the input. So sorry, no, that's again how I would design it, but it returns last. It also returns last always, like kind of jumps or caches, is like doesn't like depends on your iterator category. And we have like 4 scenarios to consider for the algorithm that we propose, that has space for some elements. I mean the output has space for some elements, has space for all elements, has space for what I call tail, and equally to tail. And this tail is basically exactly the number of elements from middle to r end. And result r is empty. With that scenarios, we answer what we propose for what to do if the range like is sufficient or not sufficient. What is our semantics? So if we have the input that is equal to 6, and then the output that is like only can take 2 elements, this is our 1A scenario. We have we can take only 2, and we take of course 4 and 5, but then result in dot in point to res. So I forgot to mention during the reverse copy design discussion that our design goal is always return past the last iterator that we were not able to copy. We basically follow the same design principle here. So it's 6. If we change the output size to be more like 5, we of course copy everything like 4 from the tail, how I call it, 4, 5, 6, but then we copy also 1 and 2, and we return the iterator to the position to the element that is equal to 3, which is again past the last element we weren't able to copy. The output is not sufficient. If it's 6, we return exactly what invite says. So we return middle because it's past the last element, but we're able to copy everything. We like, and again, like let's start to look at the corner cases. So if the output is 3, and by the way, again, I forgot to mention that, yes, you can see that our middle is basically points to 4, like it's begin plus 3. So if it's 3, we have the place only for 4, 5, and 6. And we copy that, and design choice that what we had here is what to return. Either it's last, which is kind of maybe counted as the past the last, or is it first? And we decided it should be first because it's the next element that would be copied if the space would be sufficient. And the last scenario is when the result R is empty. In that case, we also return middle because we didn't copy anything. And in that case, like the ability to detect an error on the user side was like is the way like they can just check the output. The output, res output is equal to output begin. So we did not move or end. I mean it's the same because it's empty, right? Yeah.
Why not return last if you finished successfully?
We were debating about that, but we kind of decided to stick to the again, pass the last that was copied. Because if we envision rotate view, that's kind of how I see the design. And this is basically the answer to a question. We just go to this slide. If we imagine the rotate view, it would do the same. I mean, I'm emulating it, but I believe that if we just implement it and propose it to the standard, it would return you this kind of middle point. Otherwise, rotate view might be input iterator, like a forward iterator, and it would need to cache this last when it ends like the tail, what I call tail. Here we emulate the rotate view with drop 3 and take 3, and then concat. Concat just concats like two views. And it's from range SP3 because neither of C++ implementations so far that I tried implement concat view. I could not use it from std. But the behavior is exactly the same as we propose. So if rotate view will appear at some point, or if people would try to emulate rotate view with concat like this, it's consistent with what we propose. And I really want rotate copy and copy from rotate view work the same way. Yeah, and if we also have this corner case with 3, right, we just constrained our rotate view with 3, it again returns 4, 5, 6 to the output, writes 4, 5, 6 to the output, but also returns you 1 as the next element that would have been copied if you have enough space. Are we alive? Are there any questions? So copy if is going to be even more complicated. All right, let's go to copy if. For copy if, the design is also interesting because we basically also need to determine whether the output was sufficient or not. But copy if is special, as the algorithm with with the similar semantics. Let's look on our fascinating signature again, and let me show you the implementation that I've seen in some parallel framework, and they claim how quickly their copy if is working. So we have size, we have for each, and those slides are for demonstration purposes only. I'm not trying to make it as generic as possible. I might skip some stood forward. It doesn't matter for the purpose of this presentation. Even might be, I believe this code compiles, but I hope I didn't miss any namespaces or whatever. But still, the point is we have for each with iota, which is basically indices. Then we capture result and result R, and we invoke our predicate, and if predicate is true, we just take this index and write in what was in input in the output using this index. What's wrong with that? I mean, or is everything is fine and is it the best implementation ever?
No,
I mean, I know.
Well, you're going to write over parts of the output, which might not be actually part of the end set, right?
Yeah, Stephen, go ahead.
Well, you're copying elements into the same position they were originally in, and the elements that you're not copying will keep their original value.
Yep. Like this. And I mean, this is something, but definitely not copyIf.
No, copyIf is supposed to squash.
Exactly. So it's like gather algorithm. Yes. So basically for this input, we're supposed to have and this predicate basically does the odd numbers. And the output that was originally filled out with zeros, we're supposed to have 1, 7, 5, 3, 7, 9, but we have like this. Of course, it's fast, but it's incorrect. So what's the point of having this algorithm? Okay, let's imagine how we parallelize copyIf. David, I know you know how to parallelize it. So any ideas?
I haven't done it, so I have some ideas, but I'm not sure.
Okay. So yeah, basically we have the our invocation with the given data, but I also use it as the some pictures. CopyIf is not trivial to parallelize because we need to squash those values. But what we can do is we first of all can individually compute all values, like to know the mask. And mask here is not bool. This is kind of the hint. Mask here is like int or size t or like whatever. It's like literally 1 or 0. What could we possibly do with this mask? Well, we know the answer for each individual element, which was done in parallel, by the way. Jeff?
Well, you can count up what the size of the output is going to be.
But how do we know where to write?
You could calculate partial sums up to some point.
In other words, scan.
Yeah.
Okay.
That's what we do. We scan this mask, and we have basically positions for the for the mask with 1. So when it's true, like where to write. For the last element is going to be 6, index 6. So we need like at least output for 7 size, but we have the output size equal to the data size. So we can, safely assume then it's sufficient. We just write based by the indices, and it's it's parallel for, right, or for each. And I'm not pretending that this is the best possible implementation ever. It should be correct, but it's not like the most performant one. It's just to give you the idea step by step how copyIf can be parallelized. If we have parallel scan, of course, which is also not trivial to parallelize. And also, I'm not saying, sorry. And this is kind of how we move it, but we will look in the code. I'm also not trying to say that, it might be, some algorithm might be squashed, but I also did not do that because I want you to show it like step by step. And I hope my implementation doesn't contain bugs. It might, so don't judge very strictly. The thing is, again, it's for demonstration purposes. So I simplified our fascinating signature, so just saying like it's some press, some proch, and remove requires, because again, for implementation purposes, it doesn't matter. Let's try to do something. So first of all, we allocate the array, like the vector for mask, then we transform it. So, and here I purposefully moved predicate and projection to show that this is the only place where we need them. When we calculated the mask for each individual element, we don't need that anymore. And then we just return like bool, which we check and convert to size t to store it. Then what we do, we do our exclusive scan. And you can see the ease of use that I was talking about here, because we have transform as ranges with our proposal, and you use exec, r, mask, without any begin sense, without anything. But for exclusive scan, since we don't have numeric algorithms with ranges at all, except iota, but not like the, let's say...
not the useful ones.
Yes. I was trying to find a polite word, but yes, you're absolutely right. Yeah, you should do like .begin, .end, like again, .begin, all of that. So we use the parallel exclusive scan from the existing algorithms. Then, when we have the scan, like mask already scanned, we know indices, and there is another piece of code with zip iterator. When we zip our mask and result, those are the same size, we go for each with execution and zip, and we capture result R by reference, and we write to the result using the index that we know from scan from in when the mask is true, and our true is like 1. Is it clear?
But wouldn't the zip make it non-parallel again? Like, wouldn't you?
No. And by the way, thanks for this question. We don't propagate policy to the view. I forgot to mention. We only parallelize the output, the outer algorithm.
Right. But
And
don't you lose performance?
zip is random access. Everything is fine.
Oh, okay.
We can just randomly access any elements, any element of it. Everything is fine. And as you can see, there is a blank space in between exclusive scan and zip. Oh, sorry. And yeah, I forgot to mention completely that we also need to determine how much elements we copied. So we need to return the correct iterator for in and output. And for in, for simplest case when the input is sufficient, it's obvious, like we just handle all the input, so we just return end. For the output, we need to calculate the number of elements. And the number of elements is going to be, just believe me for a moment, again, imagining that the output is sufficient. So scan of the mask, the last element, plus the value of mask itself. So in that case, it gives us 7. And when we are back to our slide, we return exactly what I said. So the size, like the begin plus size for input, and the begin of the output plus the number of copied element that is calculated exactly how I said. And the blank space between scan and zip shows you that there is a problem in this implementation. Which one is that? We haven't supported the case when the output is not sufficient. We still need to do that. So, yeah, let's just go back to this slide. It's the same as it was previously, but if we just say that the output is 7 right now, it's sufficient, and we copy like this number of elements. But what if we have like the output size equal to 4? We need to determine the place where we stop, because the next element, according to our computations, is going to be 9, but we don't have the place where to write it. So for this, what we can say is that the let's look without errors on the mask. What properties can we see? There are 2 or 3, depending how you count, interesting properties. First of all, this mask, you can see that there are some groups, and those groups, let's look on this one, right, from force. We get this group right after we have true, the last element that was true. We increment it for the next one, but we don't know whether it's true or false. And we have them all 4s until we meet the next one, which is again true. And we increment it for the next one. So as here, right? We meet 9. We now have 4, and then we make +1 because this is +1 that we have, and we have 5, and we just start a new group. I mean, it appears that 7 also fits. Then we start a new group here, which is 6, 6, 6, 6, 6 till the end. But it also means that the element that you're going to copy is the last element within each group. It's always the case. And also, there is another observation that this sequence is sorted. So we probably can use something to determine what is the, like, where we need to stop. Ideas?
Lower bound.
Lower bound?
Yeah.
Probably upper bound.
Upper bound, exactly. So it's I mean, with lower bound, you can, or maybe lower bound is also good enough if you make like +1, but I decided to stick to upper bound. Upper bound is going to find, like what we're going to find with upper bound. We're going to find the size of the output. So our size of the output is 4, right? So we just go to 5 because it's upper bound. It finds the next element which is greater than existing one. So it's 5. So we just, after upper bound, at least that's what I decided to do. Again, there might be possible implementations with low bound. I haven't thought deeply about that. And I do -1 immediately when we find the element. So I do -1, like pessimistically assuming that the size is not sufficient. Then I check myself what properties of algorithm I have, like, and there are 2 properties. Like, there might be size sufficient, and then I do +1. And I mean, of course, it can be done more efficiently. If the size is sufficient, we don't need to do this upper bound at all. But the purpose of this is just not like to write a most performance implementation, but to feed the code on the slide. That was my actual purpose. And then, yeah, there is another corner case, which we'll see after we see the implementation. If your upper bound returns you last, for example, if we have the size which is 6, we don't upper bound returns you last because it finds the first element which is greater. We don't have such. We try to find 6. We do -1, we step here, and if we imagine that the size is 6, we need to return 3, right? This is the element that we didn't fit. This is perfectly fine. This works, but there is one corner case. Yeah.
So wouldn't just using lower bound handle that correctly?
No, because lower bound, without like adding some manipulations, find you the first one in the group. It
right,
finds
but you don't need to copy those elements anyway.
No.
If you skip your.
Yeah. Okay. So our thank you for asking this. So the decision here might be made differently. So first of all, for this example, we might return this position, like this element, which would be like past the last that we copied. But it's not a good decision because, it's past the last, but this element returns false. It doesn't have to be copied. Like we don't have a requirement to copy it. So we decided to return the first element which does not fit.
So lower bound will easily get you the endpoint for the for loop, for the for each at the end. But upper bound gets you the value that you need to return.
Yeah, that's
more easily gets you.
Yes.
When I said lower bound and said lower bound, we weren't thinking about the return value from copy.
Yes.
We were only thinking about that for each.
The idea is absolutely right. I'm not like saying that it wasn't incorrect, but I mean like upper bound is like more precise because it does exactly what I need for return. For
the return value.
Yes.
That's the piece that I think we were all missing.
Yes. And thank you again for bring this up. So yes, and this is the design choice. And there is one corner case that again we yet to see why this design choice is important. So let's look in the code. So we have the same piece of code. What I do is do upper bound -1, as I said, like starting on the element that I kind of support to return. I check if it's enough space, and I could do it before and not doing upper bound at all. Yeah, Steven, do you want to hold your question for a moment?
Sure.
Okay. Then, yeah, but I just decided to do that. Then I also do this. If the last iterator, the iterator that is returned from upper bound is and -1, of course, points to the back, to the last element, and the mask then there is 0, I also need to keep that corner case in mind. And we'll see on the picture in a moment why is that important. Then I calculate the distance. Oh yeah, and sorry, I'm going back. And yes, I do plus. So I pessimistically do -1, and then I check whether I need to do a +1 back to calculate distance to this point, or I incorrectly did this -1. So, and then I calculate the distance, and I also take into account this distance here. ZipView, it apparently works that way, that it just exhausted the smallest range, and then it stops. And that's exactly what we need. And also, we need to, for return value, we need to think how to use this distance. And that's how we use it. So we basically say that scan result is distance, with the copied elements, the scan result from distance -1 and mask -1, and then copied elements still here, but now we return std ranges begin plus distance. And why this corner case is important is because of this. So we dropped our 3 at the end, and we have size 6. So with my implementation, we try to find 6, right? Because the size is 6. We are in the last position. We did -1. We are at 6. But then we check. Hey, this is not the element that we need to copy. So we make +1 again. And that means all the input is handled. That's why this design decision is important. We do not artificially return past the last. I mean, this past the last, right? Which is 2. When we know that we can handle all the algorithms, all the input, we make it more user-friendly. Is your question still there?
Yes.
Okay.
What if the input is empty?
What if the input is empty? Let's think about it.
So if you go back to your code,
okay,
you see on auto last iterator, you're taking -1 of the end iterator, which is also the begin iterator, because mask and scan results will also be.
As I said, my code can have bugs.
So I think if you do the check for end, check if the upper bound returns end rather than checking size after.
I mean, if we put the example, we can just, return at the very beginning.
Yes,
again, the purpose is to feed the code on the slide.
Yes.
And show the idea. It's not the fully conformant, most performant implementation in the world. But at least I hope you guys get the idea. And yes, we stopped talking about copy if. Are there any questions, or shall I move on?
Well, it's just a statement. I'm glad you're writing it, not me.
Yeah, and I mean, I haven't showed you the size of the proposal, just it's huge, and some of the guys here just saw it. Okay, this was the most complicated part of the talk, and now we're going to relax a little bit. So this is for each yet another category, and we were trying to determine the the return type for each. And as you can see, we have a zoo here. But actually, if you think about it a little bit more, it makes sense. Everything except stood for each end. I don't understand, and I don't have explanation why is that. But let's go one by one. Stood for each returns function. It's pretty logical, right? Because it has the it doesn't need to return iterator. Users already have begin end, and this is existing. Sorry, I misclicked. So this is existing algorithm. I mean the serial one, and it has like the same iterator type. So yeah, and function is taken by copy. Users might accumulate something there, and they just don't want to use reference wrapper, and they get this function back.
Right. The sequential stood for each. The function object can be stateful.
Can be stateful. Yes, yes, that is correct. In parallel, we return void because it technically can, but should not. And yes, better to say it cannot be. Users should not rely on the fact that they can accumulate any state in parallel world, because in parallel world we want to make as many copies as necessary of this function object. For each n, it returns iterator. It's logical. This part is logical because it has n as the bound, but we might not have this iterator back when the algorithm stops, if it's like forward, let's say. So it's good to return it, but why doesn't it return a function? I have no idea. I mean, there is nothing wrong for each n to have like stateful function as well. So it kind of forces the users write like reference wrapper to call the algorithms. Okay, I have no idea why is that. For parallel state for each, we return iterator for the same reasons, and we don't return function for the same reasons as just for parallel for each. And for ranges, as I mentioned earlier in my talk, we return both iterator and function, because again for each we might not have an iterator at the end of the call. We have sentinel, which is not the same, and function still can accumulate some state. Based on that, we came to these design choices. I mean, we could choose void, but we kind of believe that being closer to range algorithms is important. We drop function from all the overloads that we are adding, and we still return an iterator, like just in case users want to save it or whatever. And we don't return function for the same reasons. Like we want to make as many copies as we need, and users should never rely on the any state accumulation in the in lambdas that they pass to for each. Okay, we covered every major design aspects, I believe. And now let's talk about heterogeneity a little bit. And this is kind of a small overview, because the talk with parallel algorithms and heterogeneity is a very big topic, which requires yet another probably 90 minutes or even more, depending on what you want. But we have our implementation of parallel algorithms, oneDPL, that I mentioned today already. It's our implementation, and by our I mean made by Intel. It's an evolution of the product that formerly, like former parallel STL, which we donated to LLVM, and now it's used as the GCC implementation of parallel algorithms, like GNU libc, C++, better to say. It supports heterogeneous computation, heterogeneous algorithms via SQL, and again, like I'm not going to talk about SQL today, but just briefly, it's language for heterogeneous computing. Right now, oneDPL is part of the UXL Foundation, so we have an open spec, an open specification. So in principle, anybody can go and implement oneDPL according to the spec, and the source code also belongs to UXL Foundation right now. So from what we propose, we have like 40 parallel range algorithms approximately available as an experimental, but only heterogeneous implementation. And now we start moving more and more to product quality, but unfortunately today resources, like we don't have enough resources to move like in the fast pace, so we just do it like piece by piece. And now 20 algorithms are available as the product quality, both for just host execution or CPU execution, if you like, and like heterogeneous execution. So I hope you still remember this example that we looked at the beginning with our pipeline, data, transform, reverse, and find if. So what it would cost to make it work in heterogeneous environment. So we need a SQL queue, and basically this is the abstraction just in a nutshell that allows you to associate a device with. And your device can be GPU, and probably it would be better to write like queue out of like GPU selector, but it's some, queue with the default SQL device associated with that. Then we need an allocator, because heterogeneity is about like data accessibility. I mean, parallelism and also data accessibility. So data should be accessible on the host and on the device. I mean, might be only available on the device, and it depends on your use case. But for the purposes of this example, we are going to make it like available on both the host and the device. We create an allocator type, which is our USM allocator, and USM is a unified shared memory, which is accessible like from both host and the device. And we pass queue, basically associating the device like with this like our queue with this allocator. Then we create a vector from this allocator, but we also need to create a subrange, because right now we just don't support vector directly, specifically for heterogeneous use cases. There are some problems with like copyability of vector to the device, so we need to create a view. You can use span, like whatever, span or subrange, but you need to use view. And then you need to pass it to parallel algorithm like this. So our data becomes not the vector, like our vector is v, our data is subrange, we pipe it with transform, with reverse, and then we change the namespace to make it like DPL find if, and also we make an execution policy, which is our specific device policy, which is also associated with the same queue as the memory. So you make this association of memory, device, like, and you can pass it to the invocation. But then it works fine. What about performance? We have some performance data. Basically, what we did is like we have two chars, but I'm going to show only one. We run it with 16 million elements, like this example that I've shown, and with 268 millions. And what we use there is like host execution and heterogeneous execution. For host, we use TBB with Intel Xeon, like 2-socket Intel Xeon, 56 core each. And also we use SQL with like our GPU data center max on one tile. And this graph shows you like, and yes, we did it like 100 runs and took a median. So this graph shows you a speed up compared to serial algorithms. So first, parallel, like 3 calls that we have at the beginning, like what we have, like transform, reverse, then find if. With 3 calls is like 10 times faster than serial. With 3 calls with ranges, about the same number, like 11 times faster, about the same number. Again, like ranges, but not piped. Again, 3 separate calls, like transform, reverse, and find if. And also, like when we piped it and make it a one invocation, it's 30 times faster. And for GPU, like 3 algorithms call, we have like 66 times faster. For both like 3 separate calls, iterators based, ranges based, and 106 times faster if we pipeline it. So looks promising, right? The only disclaimer is we basically don't have reverse implementation yet for like host. We needed to emulate it, but the results were as we expected. Yes.
So is the sequential baseline using the same variant that each of the sped up versions is?
What do you mean by that?
I mean, so
is the sequential version the exact same code but with the sequential execution
Yes.
policy?
Yes.
Or
Yes.
with the non-parallel
Like we tried to make it as close as possible. I asked some guy to collect this data, but I'm pretty sure it's like it should be either the same or very close.
Yeah. So each speed up is against a different baseline.
Each speed up is against sequential one.
Yes, but each of these bars has a different sequential baseline.
Yes.
I'm not following.
You did the iterator approach sequentially, and the range approach sequentially, and the parallel range pipeline sequentially. So you have 3 baselines that you're comparing 3 things against.
Oh no! Like it's one baseline.
Okay, so what is the sequential code that is comparing? So that does that mean that the say the pipeline parallel range API is about 3 times faster than the others?
Yes.
In actual time.
Yes.
Okay.
Yes. Okay. So we have no other questions. So let's wrap up. But I mean, wrapping up is not going to be fast either. So let's look into this slide. I mean, I don't want you guys, of course, to remember all the algorithms that I'm showing. But the purpose of this slide is to show that what we had in C++17 with execution policies, we add this. Except, of course, numerics, because we don't have numerics and ranges. But this is what this slide is saying. We also add new algorithms that are only in ranges. Like we didn't have them with execution policies, but they are either expressible with the existing one, or they are the same, but the direction is different, right? We have find, but now we have find in existing one, but we have find last in new one. And I mean, it's just starting from the end, and that's it. So we have a clear guidance from the existing algorithms. And what is out of scope? And the out of scope is the algorithms from C++17 that didn't have execution policy. Those are, for example, lower bound. For example, binary search. What is the point to parallelize them? Or some non-logarithmic algorithms, but which do not make sense to parallelize. I mean, hard to parallelize and don't really give some performance benefits. Or like the parallelization benefits is yet to be proven and we don't envision immediate use cases. Anyway, if somebody brings this up, we can always add them later. No breaking changes here. Algorithms from numerics, as I mentioned, we are planning to do that, but we don't have even serial range, numeric ranges algorithms, how David says, like the useful one so far. And also other algorithms in namespace ranges, besides something that I already mentioned. So it's fault family. It's if I'm not mistaken, it's specified to be sequential by nature right now at least, and generate random, which is special for random number generators, and we don't have execution policy, and so far we don't see a reason. If at some point we see the reason, we can extend it, sure. Those the categories that I promised. So basically, what falls out to the categories that we discussed. So for copy, like an initialized copy that we discussed, we have also move, transform, replace copy if, partial sort copy, initialized move, and merge. Merge is a little bit different, but it's close enough to this semantic. Special algorithms, reverse copy, rotate copy. We discussed that. Yeah, those are special. So algorithms, output and gaps, like copy if. We have remove copy if, unique copy, partition copy, and all set algorithms. Union, intersection, difference, and symmetric difference. And for each, lonely for each, which we discussed, the return type 4. And this is the oneDPL status to just give you an idea of what we have implemented. All of, any of, none of, for each, not for each n, by the way. Find if, find if not, adjacent find, and others like copy, search, min element, max element, merge. And that's what's coming. Like, basically fills the gap to this like similar algorithms, I believe, like replace if, remove if, is sorted until, min max element, like other finds, mismatch. So, and also min max and min max. Those are also coming like from the new set of algorithms. And I mean, they should be available in the next release. And the proposal status. So design is approved. We successfully passed SG1, concurrence and parallelism, SG9, ranges, and LEWG, Library Evolution Working Group. We are actively reviewing this proposal in the Library Working Group, LWG. And it still has the opportunity to be included in C++26. I strongly believe in that. We should do that. Jeff, we should do that.
I mean, we're so close.
We are close, yes. We made the first pass through the wording. Further work, numeric range algorithms. Yes, we miss them. We need them, and probably I'll do my best to have the paper to Bulgaria for C++29, of course, like together with NVIDIA guys like Mark, which all the committee guys know. Synchronous parallel algorithms, senders and receivers, P2500. Another my paper, which, we stuck on the design, but we get back to it. Asynchronous parallel algorithms, which everybody waits for. It's like NVIDIA paper right now, but I hope we're also going to have like fruitful collaboration on that and also bring those in like C++29. And our stretch goal is probably to add range as an output for serial range algorithms. But, I need to focus on first three first, because that's kind of my job. And probably at some point, or if somebody willing to, I can help, but, not my focus right now. And useful links. I'll keep it for a moment if you guys want to take a picture, but also, I'll send it in Discord anyway, and you can just, see the slides like in the Discord. And the final slide that I have for today, while I'm waiting, yes, Steve made his picture. Let's give a special thanks. Special thanks goes to Alexey Kukanov. This is my co-author, who put a lot of effort to this standardization effort. I mean, not as much as me, but still a lot. And I mean, yeah, he was very helpful during paper work and still keeping being helpful, and also during this talk preparation and improvement. With his help, we improved this talk drastically, and I hope you guys enjoyed it. Jonathan Müller, next special thanks for objecting to range as an output design aspect. Because of that, we went into the standard and basically work through this design aspect deeper and understand it better, and were able to return back and convince Jonathan and the rest. We wrote a separate paper, and also because of that, Jonathan helped us with reviewing wording and found one design bug. Thank you for that. Inbal Levy, this is another special thanks for when we weren't able to schedule it in Poland. Inbal set up out-of-cycle telecom, and we reviewed it, and because of that, we were able to move it in Austria on our next committee meeting. Without that telecom, I believe it wouldn't be possible to even have chances to land it in C++26. Next special thanks go to Jeff Garland and Jonathan Wakely to put it in the schedule between Austria and Bulgaria on telecoms. So we're still reviewing them actively, and we still keep save chances, save this proposal for C++26. And the next special thanks goes to Zach Lane, and again, Jonathan Müller, for reviewing the abstract and providing me a very useful feedback on the abstract. And the feedback was, the abstract looks good as is. Yes, we don't have time for some bonus example that I made in case the time remains. But when I did my dry run yesterday, I realized that no, it's not realistic. But you can see it on the slides which I share. I'm not going to remove it. That's all that I have for you guys for today. And thanks for attention. I mean, we probably have 30 seconds for questions. But, if you have anything to ask, you're welcome. Otherwise, I'm happy to discuss any other questions that you might have after this talk.